So, in layman's terms, what is PWM? PWM stands for pulse width modulation. It's also sometimes called pulse width demodulation, so PWD, but most commonly it's called PWM. So what is this PWM thing? Well, in order to explain this, I'm going to use a real-world example that hopefully we can all understand. The example I'm going to use is an electric oven. Now, it's not your normal electric oven that's got a dial on it for the temperature and a thermostat inside. It's just a box with a heater. And I've got a switch that I can switch the power on or I can switch the power off to this oven. Now, of course, if I switch the oven on, it's going to, over time, heat up to its maximum temperature and stay there. And if I switch it off, it'll cool back down again to room temperature. Now, if I were to switch it on for 5 seconds and then off for 5 seconds and then on for 5 seconds and off for 5 seconds, and I were to keep doing that, over a longer period of time, only half the amount of energy will be getting into the oven. It's not on all the time, it's only on 50% of the time. So it won't reach its maximum temperature. For the sake of this example, let's say it reaches about halfway to its maximum temperature. It's only got half the power after all. If I were to, for example, switch the power on for 1 second and off for 9 seconds, and then on for 1 second and off for 9 seconds, it would only be getting 10% of the amount of energy that it would at full power. So it would only heat up to about 10% of its maximum temperature. The same is true if I were to hold the power on for 9 seconds and then off for 1 second, and then on for 9 seconds and off for 1 second. If I were to keep repeating that, it would get close to 90% of its maximum power. So what am I explaining here? How does this work with PWM? Essentially, that is PWM, pulse width modulation. The cycle time or the frequency of our PWM signal, in this case, me holding the switch, is a period of 10 seconds. So if I switch it on for 9 seconds and off for 1 second, then its duty cycle, how long it's on for, is 90% of the whole 10-second cycle. Or the same if I hold it on for 1 second and off for 9, then the duty cycle is 10% of the whole cycle time. And every 10 seconds, the cycle repeats. So your PWM frequency, in this case, is the period's 10 seconds, so that's 0.1 hertz. But your frequency of your PWM, it depends entirely on what the application is. For the sake of an oven, then a 10-second period might be fine. But if you're running a motor, for instance, then that motor is going to accelerate and decelerate each time you turn the power on and off. So for a motor, you might want to run the frequency of your PWM, how fast, how often you repeat the cycle, maybe at 50 hertz. So you might want to run that 50 times a second. So the period where you're going to start the cycle again is 20 milliseconds. And the duty cycle is then within that 20 milliseconds. That way, with a motor, you'll get smooth speed control. So PWM is essentially used to give you a variable control over something when all you've got is an on-off switch or an on-off mechanism, electronics, microprocessor. However you're going to drive that PWM signal, it's one signal, on or off, and how big the pulses are in your pulse width modulation dictates how much energy gets put through to the device. For example, if you were controlling the brightness of an LED, a 50 hertz PWM signal is perfectly sufficient because our eyes can't pick up the flicker at 50 hertz. In some instances, you might want to be running it much, much faster. So that is what PWM is, pulse width modulation. You can control the amount of energy that goes into a device using this mechanism, and you can also communicate information this way using just one wire. If one device is transmitting a PWM signal and you know what frequency it's running at, say 50 hertz, then on the other end you can read those signals and measure the time that the output is on for, and you'll get a 0 to 100% value that the other thing is transmitting. So it's also used for communicating information. So that's what PWM is. Let's have a look at what PWM looks like on an oscilloscope. Okay, so here we have a PWM signal running on an oscilloscope. This is coming from a microprocessor, and essentially at the moment it looks like a square wave. We can see here we've got 5 microseconds per division here, and we've got exactly 2 divisions before the cycle restarts. So that's 10 microseconds. So we're running this PWM example here at 100 kilohertz. So that's how often the cycle repeats each time when the signal goes on is 10 microseconds from the last time. This is currently running at 50%, and if I, for example, change that to be 25%, you can now see that the duty cycle is on for 25% of the cycle time and off for 75% of the cycle time. Same is true if I set it to 1% or 99%. Now you can see the signal is on, so it switches on here and it's on for 99% of the cycle time. So the duty cycle is 99%, and then it switches off just 1%, and then it switches back on again. Okay, so that's it showing your duty cycle, and if I just run this, you can now see that PWM is varying from 0 to 100% and back to 0 again, and it's just cycling through those signals. Again, the period or the cycle time remains constant at 100 kilohertz. It's only the duty cycle within that cycle time that is varying here. It gives us the varying amount of energy. So that is PWM.